This video builds on the ideas of the principle of superposition and interference to look at what we're going to call two-source interference. In other words, what happens when we have two sources of a wave and those waves meet and interfere. The picture that you've got in front of you is the two-source pattern that you would get from water. And what you're looking at are two sources of wave connected together. And what we would do to recreate this image is we'd have a shallow tank of water and we'd have two little dippers connected together, and they would vibrate up and down and they would produce the ripple waves that you can see in that image, in much the same way that if you dropped a stone into a pond of water, you'd see the rippling out of those waves. And so you can see down here, can't you, the kind of waves rippling out from this source here. And you've got patches of light and dark. They correspond to shallow and dark water. So the distance between each of the light patches or each of the dark patches is equal to the wavelength of those waves. Okay, shallow to shallow or deep to deep corresponds to trough and peak to peak. So the spacing between those is the wavelength. But I'm interested in what happens when the waves meet, and that seems to refer to the zone in this little region here. And I don't know what you're noticing, but I'm noticing there are actual patches of kind of still water here and here and here and here and so on. Okay, and that corresponds to destructive interference. So when the waves from the two sources are meeting and overlapping, we are getting destructive interference. So we're adding the displacement from each of the two sources of wave, and they are effectively cancelling out. In between, I'm noticing that the bright and dark patches are more obvious than they were below when we were looking at the individual waves. And these are regions where we've got constructive interference. Okay, so the deep part of the water is deeper and the shallow part of the water is shallower than when we just had a single wave. So this is two sources of interference for water. We get exactly the same for sound. Okay, and when I'm back, I will show this to you. I'm going to get you guys to walk in a line in front of two loudspeakers. And what you're going to notice is that you get constructive followed by destructive and a repeating pattern of constructive and destructive interference. Okay, now what does that sound like? Because it's not water we're talking about now. It's going to sound like loudness and quietness repeating. Okay, so how do we show this kind of from a diagram perspective? Let me have a go at trying to recreate this with you, and you've got your own copy and you can recreate this once you've watched me doing this with you. Okay, two sources of wave, and each of these lines is a wave front showing you the peak of the wave. And so therefore the spacing between them must correspond to the wavelength of those waves. And you've got that region in the middle where the waves from one source and the waves from the other source are overlapping, they're meeting, and we're going to apply the principle of superposition and we're going to look at the interference that we get. And I'm going to first of all choose that meeting point there. So we've got waves travelling out from source 1 to that point, and I'm going to call that distance A, and we've got waves travelling out from source 2, and they're going to travel outwards, and I'm going to call that path B. Now, just visually, and you could get a ruler on this, the distance travelled is greater for path A compared to path B, isn't it? Okay, B is a longer distance compared to A. Okay, I'm going to introduce a new term to you now called path difference. Okay, path difference is the extra distance travelled by one wave compared to another. Okay, it's the extra distance travelled by one wave compared to another. I hope you can read my writing. Okay, so is there a path difference between A and B? Is there an extra distance travelled by A or B? And the answer is yes. The question is, what is that path difference? Well, the way I can work that out is I can say from source 2, we've gone 1, 2, 3, 4, 5, 6, 7, 8 wavelengths along. So B is 8 lambda, lots of distance. Whereas from source 1, it's 1, 2, 3, 4, 5, 6. Path A is 6 wavelengths long. Okay, so there is a path difference of 8 minus 6. There is a path difference of 2 lambda. Okay, now what are we going to observe at the point where the waves meet? We are observing a peak meeting a peak. And when peak meets peak, that's the language of constructive interference. And that's what we're going to observe at that point, constructive interference. Okay? Now, let's pick at a different point. Let's pick that point there. Okay, and I'm going to do a similar process. Okay, there's the path taken to get to that point from source 1, and there's the path taken to get to source 2. Okay, going to call that C and D. And I think by eyeballing those, you would say that actually C and D are the same length. So there is no path difference. There is no difference in distance travelled by C and D. What are we going to observe at that meeting point? Well, it looks again like we've got the peak of one wave meeting the peak of the other wave. So we're going to notice, again, constructive interference. Okay? Right, one final one, and then we'll make a little summary. Now we're going to choose the meeting point to be there. Okay, so there's the distance travelled from one source. There's the distance travelled by the other source. I'm going to call that E, and I'm going to call that F. Okay, obviously E is greater than F. Okay, shall I just change colour because that looks like that might be quite difficult to see. So let me just go back over those lines again just in case they're not kind of appearing very clearly to you. There we go, E, F, there's the meeting point. Okay, E is greater than F, so there is a path difference. Let's work out what that is. So from source 1, 2, 3, 4, 5, 6, 7, and it's halfway to the 8th. So we've got 7.5 lambda is the path taken by route E. Okay, path F, 1 wavelength, 2 wavelengths, and 3 wavelengths. So F is 3 wavelengths because it's the peak that I've reached at that point there. So is there a path difference? Yes, there is, but this time it is 4.5 wavelengths. It's now like 4.5 of a wavelength. Okay, so what are we going to observe at this point? Well, I've got the trough from wave E meeting the peak of wave F. It's a trough meets peak now because the point that I've chosen is in between the two peaks from source number 1. So I'm actually going to observe now not constructive, but destructive interference. Okay? And that's going to lead us then to a rule for whether we get constructive or whether we get destructive interference. Okay, before we move on, here's another set of language that you could use. We could say that here the two waves were in phase. Peak meets peak, trough meets trough. Equally, we could say the two waves were in phase. However, for the E and F roots, we are going to need to say they are in antiphase. And hopefully you'll recognize that that's how we described constructive and destructive interference when we looked at this in a previous video. So you've basically got two pieces of language now for describing constructive and destructive interference. We can either use the language of phase or we can use the language of path difference. So here is your summary. In order for there to be constructive interference, the path difference must be a whole number of wavelengths. So if we go back to the diagram that we drew, when did we observe constructive interference before? We observed constructive interference here, where there was a path difference of 2, and we observed constructive interference where there was a path difference of none. Okay, I would have also observed constructive interference if the path difference was 3 lambda, 4 lambda, 5 lambda, 6 lambda. In other words, n lambda path difference gives you constructive interference. In other words, one wave has had to travel a complete extra amount of wavelengths compared to the other one. But for destructive interference, they need to be in antiphase, and the way that we achieve that is a path difference must be half a number of wavelengths different. And again, that's what we had with E and F, wasn't it? They were 4.5 wavelengths different. So the way that we would summarize that is a path difference needs to be n and a half. We've got to add on that half bit of wavelengths different. Okay, so that is your argument in terms of path difference. However, we could also argue in terms of phase, and we could say that the waves need to be in phase for them to be constructively interfering, or in antiphase for them to be destructively interfering with each other. Okay, it's two pieces of language to describe constructive and destructive and constructive interference, either in terms of path difference or in terms of phase difference. Okay, now let's look at a practical example then of this, and that might just help you to make sense about this if you're struggling a little bit with it. Okay. Two speakers connected to a common source emit sound of a certain frequency of a certain speed. One speaker is 24 meters behind the other, and a listener stands 68 meters in front of the nearest speaker. Draw a labeled diagram. Good idea, because there's quite a lot happening here. So I've got two speakers, and it says that one is 24 meters in front of the other one. Okay, and then we've got a listener, and the listener is 68 meters in front of the nearest speaker. Okay, so that's the labeled diagram setup. Okay, right, express the distance from each speaker in terms of wavelength. Okay, now I don't know the wavelength of the sound, so that's going to be my first job to work out then. So I'm going to use the wave speed equation. Okay, wave speed is wavelength times frequency. I want to know what the wavelength is. That's V over F. So that's 340 meters per second divided by 1700 hertz, 0.2. Okay, so a complete wavelength is 0.2 meters. And I'm being asked to express the distance from each speaker in terms of wavelength. Okay, 0.2 meters is a fifth of a meter. So I get 5 complete waves in a meter of distance. So if you work this out then, I'm going to get 120 complete waves in 24 meters of distance. And similarly, I'm going to get 340 wavelengths fitting into a distance of 68 meters. Okay. So how have I arrived at those two numbers? I take the total distance, 24, and I divide it by the distance for one wavelength, 0.2. Okay, so now I've expressed each distance, not in terms of meters now, but in terms of wavelengths. Question 3. What is the path difference? The path difference is the extra distance that one wave has travelled compared to the other. So one of the waves has travelled 340 and the other has travelled 120 lambda. Okay, that's the difference in distance that one has had to travel compared to the other. In other words, there's an extra 220 wavelengths that one of the waves has had to travel compared to the other. Okay. Question 4. What will we experience? Okay. If the path difference is n lambda, we get constructive interference. If the path difference is n½ lambda, we get destructive interference. Now I'm looking at this 220 value here, and I'm kind of going, it seems to match that criteria there. 220 is an exact integer number. N is 220. So in other words, we're going to get constructive interference. Question 5, what will the listener hear? Now you might think, well, that's exactly the same question, but it's not quite. Okay, constructive interference is the kind of the physics behind what's happening. But actually, what will you hear? You will hear loudness, because that's what constructive interference relates to. Okay, if it had been destructive, it would have been quietness. Okay. Final question. What would a listener hear if the frequency were halved? Okay, if the frequency is halved, then the wavelength is doubled, okay? But we would still have a whole number of wavelengths different between each path, okay? And if you don't believe me, you can work this out. So the new wavelength is 0.4 meters. So now the question is, how many wavelengths fit in the 24 meters? How many wavelengths fit in the 68 meters? And what's the difference between them? Okay, if you do that calculation, you will find that you get an integer number of wavelengths. Okay, you get a whole number of wavelengths different. So in other words, the person is still going to experience constructive interference, which basically means they're still going to hear loudness, but the frequency has changed. And frequency is all about pitch, isn't it? So if the frequency is halved, the pitch has halved. In other words, the frequency of that note is going to be lower than it was before. Okay? So that's an example then of kind of quantifying constructive and destructive interference. Okay, a final point then. In all of the examples that I've shown to you so far, whether it was the water or the speakers or whatever, it was really important that those sources of wave were connected together. In other words, the two dippers that were dipping into the water had to be connected together. The two loudspeakers that you're going to walk in front of when I get back, they have to be connected together. And there's a reason for this. We need both of the sets of waves that are produced from our sources of wave to have the same wavelength and therefore the same frequency. Okay, but we also need there to be a fixed phase difference between them. Okay, a fixed phase difference between them. Okay, what does that mean? If this is source A and this is source B, we would say that they are in phase. Okay, peak meets peak, trough meets trough. Okay, so what is the phase difference between them? Well, it's zero. There is no phase difference between them. And it is zero here, and it is zero here. In fact, the phase difference is zero at whatever point along the wave I consider it. So that means I've got a fixed phase difference between the two. Okay? Similarly, I could have a source of wave that looks like that, and I could have a source of wave that looks like that. You would say that's destructive interference because peak meets trough and trough meets peak. Okay? However, there is still a fixed phase difference between them. Okay? We are half a wavelength out. We're 180 degrees out of phase. 180 degrees out of phase here, 180 degrees out of phase here, and 180 degrees. We're a fixed phase difference between the two waves at all points. Okay? So if we can achieve these three things, okay, which is to have the same frequency, the same wavelength of wave, and if we can ensure there's a fixed phase difference between them, then we can describe these interference patterns that we get sorry, let me backtrack. We can describe these two waves as being coherent. Now, why is that important? It enables a stable interference pattern to be seen. So let me illustrate that on a static slide, and then I'll show you something that's animated. Okay, so on the left, you've got two waves. They are in phase, and they are always in phase. Do they have the same wavelength? Yes. Do they have the same frequency? Yes. I mean, they have to. Is there a fixed phase difference between them? Yeah, it's zero phase difference at all points. So they're coherent, in other words. Okay? Even the diagram on the right is coherent. Okay, do they have the same wavelength and frequency? Actually, they do. Okay, now they are a little bit out of phase, but is the phase difference fixed? It is. Okay, and that phase difference is being shown by those dotted lines. Okay, the spacing between those pairs of dotted lines is remaining the same, and so therefore those waves are also coherent. And that's important in order to achieve a stable interference pattern. So let me show that to you here. Okay, I need that to be true. Okay, the red and the blue wave are coherent. Same frequency, same wavelength, and there is zero phase difference between them. Okay, there's a fixed phase difference, and the resultant in pink is a stable interference pattern. Okay, if I now change the blue wave and now it is no longer, there we go, it is no longer the same wavelength anymore. Okay, now look at the resultant wave. That interference pattern, okay, is not as what we call stable. It's not as clear as it was before. we would describe those two waves as now being incoherent. Okay, and so if I keep changing the wave length of the two waves, you can kind of see it's oscillating according to both the red and the blue wave, isn't it? Okay, that is not as clear an interference pattern. And so when we're looking at two source interference, we always want coherent waves. Okay, and we'll have a look separately at how we achieve that. Okay, that's all I'm going to do on this bit with you. Okay, so please review this material again, and then we will pick up on the idea of two source interference from a practical perspective when I'm back in and in front of you.